Okay, thank you all for being here. I'm Lorenzo Rovida. I'm a visiting student from Italy, and I will present this work, which is a joint work with Alberto Leporati and Simone Basile, and it's a work about sorting values in FHE. So, yeah, I already spoiled it, but let's start with a story, and let's start from our alien friend who is visiting us. And they're asking us something which translates to, can you sort my deck of cards? And I mean, this is a likely situation, and you say, okay, of course I can help you. The issue is that these cards are really not readable. So the question is, how can we sort them even if we are not actually able to read these cards? And a little bit more boring and formally, the question becomes, how do we sort values in an encrypted domain? So we know that these sorting algorithms are crucial to many algorithms, applications, and so on. But the thing is, most of the most used sorting algorithms are data dependent. So this basically means that we can always define best case, worst case, and so on. And the flux of execution of these algorithms depend on the input data. While in FHE, we cannot really do that because we cannot read these cards. So we have a lot of ciphertext, but we cannot really read them. So the question is, how can we sort values which are encrypted using oblivious algorithms? And oblivious algorithms are these kind of algorithms whose set of instructions is always constant and doesn't depend on the input data. Currently, the most used approaches in the FHE world are network-based sorting and permutation-based sorting. So concerning the network-based sorting, I will go with an examples later, but we have this network, which is composed of a lot of compare and swap operations. So this compare and swap operations just is an operation that corrects pairs of values depending on the ordering. While the permutation-based approach, which we'll see now, deviates from this paradigm and somehow doesn't want to continuously compare and swap values, but it's just about, okay, we have a vector, let's try to build a permutation matrix such that when we perform this multiplication, we get out the sorted vector. We have some reference works. For the network-based approach, we have an example from TFHE, from some COSIC people, actually, which is a top case selection, and also another work, which is a Bitonic network based on CKKS. And I will go back later on this thing, I like that we will need n slots to perform comparisons and to sort these values under the network-based approach. While on the other hand, we have the permutation-based approach, and we have a single example, which is a very recent work where they propose this permutation-based sorting, and it requires n square slots to be able to compute them efficiently. So yeah, to summarize these two approaches, we have permutation-based, which is a shallow circuit, but it requires many slots. And on the other hand, we have the network-based approach, which is a deep circuit, but it requires just n slots. Okay, well, just a quick slide about the CKKS scheme. I assume most of us are already familiar with it. We can consider it as a black box where each ciphertext encrypts a vector of complex numbers. We will assume real numbers for the sake of this work. And the computations are additions, multiplications, and rotations. And all the computations are performed slot-wise, so with SIMD computations. So that's all we need for the CKKS scheme. Okay, I will introduce now this permutation-based approach, introducing MIHP 25, which is a very recent work, which is actually just based on two phases. So we have the first phase, which is the indexing phase. So we have given a vector like 5097, and we want to compute its indexing. So the indexing, which I called S, don't ask me why, but the indexing is telling us the position of each element in the vector V in the sorted vector V. So maybe with an example it's better, but if we look at 5, and in the indexing we have 2, this means that if we sort V, 5 will be in position 2. 0 will be in position 1, 9 will be in position 4, and 7 will be in position 3. So this is the indexing vector. And once we have this indexing vector, we want to construct this permutation matrix out of this indexing vector, which is almost a simple task in the clear data, because if we have a 2, then the first column will just have a 1 in the second position, and so on. So it's just 2 steps, actually. So how do we compute this indexing without requiring nonlinear functions? Without requiring conditional statements, actually. So we have given V, and as a first step, we want to compute how many elements in V are smaller than Vi. So we do this phase for every element Vi. So we compute the difference between Vi and Vj for all the j in V, and we compute a sign, where the sign function is defined as 1 if the input is positive, 0 if it's negative, or 0.5 if it's equal to 0. So this 0.5 term is added to correct this bias introduced when we compare like Vi minus Vi. So we correct this 0.5 thing. So we, again, follow the example from before. We have 5097, and if we concentrate on this first term, we are just computing the difference between 5 and all the other terms in the vector. So we are computing 5 minus 5, 5 minus 0, and so on. We sum all these signum functions, we add 0.5, and we get out our indexing. Notice that we are computing actually n-square signum functions, which is an anticipation of the fact that we can parallelize all these things in a SIMD computation requiring n-square slots. That's a nice question. I'll go to it in a few slides. So the second step is to compute the permutation matrix. And we will use this equal function, which is 1 in the origin and 0 otherwise. And we just actually, following the example, if we want to compute the first column of the permutation matrix, we compute the difference between the indexing vector and a vector composed of just ones. And notice that we'll have a 0 as output right in the position where we had 1. So we just apply the equal function there, and we obtain our column of the permutation matrix. So just repeat this procedure for all the columns, so for n times, and we get out our permutation matrix. Yeah, the thing is, this approach doesn't really fit as it is repeated elements, because if we put 7, 8, 8, 1, we'll get that indexing, which is not what we want, actually. So there are 2 news. The first one is a good one. We can almost easily fix this. It doesn't have any impact, actually, in the depth of the circuit. And the idea is to compute a sort of offset where we correct that indexing with this O, which actually takes the first 3.5 and brings it to 3, and the other, it is brung to 4. So we can correct this. But the bad news is that too many things, so you can find this algorithm on a paper, but I won't discuss this now. Okay, so I presented this thing, yeah?
Why did you choose 0.5? Can't you just put it to 0 to 1?
Yeah, you can just put it to 0. It will be convenient afterwards, because then when we use the equal function, the equal function is 1 in the origin, and we want to put, so if we go back, we want precisely this value to be mapped to 1. So if the indexing would start from 0, then I'm not quite sure this would work the same. But it's just a bias. So.
Copy the wrong one. Your permutation matrix will not be a permutation matrix, but still you will copy the right elements, right?
Yeah. I mean, you might tweak the algorithm to work also if we start from 0, 1 to 3, I think. It's not a big deal. yeah, that's another thing we will discuss in a bit. Because that is a hot topic, actually. So, I mean, I presented this framework abstracting from anything, and I was presenting it by saying, okay, we use the signum function, we use the equal function, that's fine, but we all know that in FHE we can just compute additions and multiplications, so there is something wrong in all this. So we can actually use these SIMD schemes to parallelize many computations, and that's fine, but we have two main obstacles right in front of us, which are precisely the signum function and the equal function. Okay, so quickly I will introduce this nice tool, which are Chebyshev polynomials, and the thing is, if we pick d+1 Chebyshev roots, and we perform a polynomial regression over these roots, then we can find an approximation for a nonlinear function, which is not the best, but we have some results that say that is logarithmically far from being the best. This means that we can easily use these Chebyshev polynomials, are not that bad, are not the best, but we can compute them pretty easily. And also, if we define polynomials in the Chebyshev basis, with respect to the power basis, we have coefficients that will not explode or vanish. So they are very convenient. And also, we have a very nice adapted version of the Paterson-Stockmeyer algorithms to evaluate them under CKKS with a low level consumptions. So they are nice. The thing is, if we try to apply Chebyshev polynomials to the signum function, we'll get a polynomial which behaves like this, which is something that we don't really want. And if we look at the position of the regression points, it's kind of easy to understand why, because there is that large jump in the origin, which is something that we want to avoid. And a way to tackle this is to, instead of using the signum function, we can use a sort of scaled version of the sigmoid function, which is smoother around the origin. And we can control this smoothness with a k parameter that we define there. And this is an example of some points distributed according to the Chebyshev roots with k equal to 25. And notice that if we let a polynomial pass through these points, we get something which is definitely better. So this is a polynomial. We can compute it with additions and multiplications, and that's fine. And OK, now you might say, yeah, but what about the values close to the origin? That's fine. And in fact, this approximation doesn't really work well with values approaching the origin. But we will make assumptions. And we might say, I don't know, I assume that my inputs are never at a distance larger than, smaller than delta, where delta can be like 0.01. So we know that when we compute the difference between two elements, this difference will never be smaller than delta. So actually, we are interested in approximating, if I go back here, to approximate from -1 to minus delta and from delta to 1. Then, of course, I might choose delta according to what I need, and I will have to adjust k and d accordingly. OK, the last thing that I have to care of is 0, because 0 lies in that interval, but still I want a nice approximation of 0, because when I compute the difference between the same element, it will go to 0. But from that, we can easily prove that the value of 0 will always be 0.5 because of symmetries and stuff. But trust me, it's always 0.5 there. So as a result, we have this kind of thing. We assume that our inputs will always be in the orange area, while in the red one, we don't really care, because by assumption, there is no difference between two elements that will lie there, apart from the origin, so apart from 0.5. The other function is this monster, because it's always 0 apart from the origin, which is 1. And if we try to plug Chebyshev polynomials here, they will explode somehow. And if we look at other works, if you look at MIHP 25, they use this function to approximate this, which is composed of, again, two signum functions. And it's nice because it also has a sort of error correction. Namely, if we have a value which is like 0.3 because of some errors, it will still be mapped to 1, so fine. But the issue is that we are computing 2 times the signum function once more, which is something that we want to avoid. So the idea is, let's try to relax this function, because we require it to be 1 in the origin and to be 0 in all the x that are in Z. I mean, apart from 0, of course. So if we assume that our previous approximation of the signum function is good, then we will use this function to compute the difference between the indexing vector, which is close to Z, and other values from 1 to n, which are Z. So the difference should be very close to Z. So actually, we are like, with this function, we are approximated, well, I don't know, minus 1.5, but it's very unlikely that we will put minus 1.5 here. So we relax these constraints, and we can use actually this function, which still in Z behaves as before. But this function, with respect to the previous one, is way easier to approximate. We can simply plug in Chebyshev polynomials here. Even at low degrees, we can approximate it very easily and very accurately. So this is very nice. And moreover, we don't need to use the signum function once more. Yeah. So essentially, essentially this procedure just relies on the signum function once and on the sync function, which is this one, once. So we, with respect to the previous work of MIHP, they used signum function 3 times. We are using it just once. Okay. Now we'll go through a little example, again with 5097. So assume we have these 2 encodings, which are called repeated and expanded, but yeah, if you have suggestions from this. So in the repeated encoding, we simply repeat our vector n times. And the expanded encoding would simply repeat each element of the vector n times. So we compute the difference between these 2, and we obtain which we call V delta. And V delta represents actually all the possible differences between all the elements in our vector. So the following step would be to apply an approximation of the signum function on these differences. And notice that if we pick the slots in these positions which are at distance n, now we are considering the slots, I go back, where we computed 5 minus 5, 5 minus 0, 5 minus 9, 5 minus 7. So these slots refer to the number 5, actually. And if we apply a rotate and sum algorithm, where we rotate and sum elements in position multiples of n, we get out, and we add 0.5 to correct the bias, we get out 2, which is precisely the index of the number 5 in the sorted vector. And we can actually, since we are working on SIMD computational thing, by performing this operation, we are actually computing the indexing for every element in the vector. So we have 2 for the element 5, we have 1 for 0, we have 4 for the number 9, and 3 for the number 7. And notice that is already in, let's say, a repeated encoding. And 2, 1, 4, 3 is our indexing vector. And we computed it with a single signum function operation. And to conclude, which is also a nice thing, we just have to compute one last nonlinear function, which is the sync function. And we're going to apply it on the difference between our indexing vector and another vector, which I call 1 to n. But we simply pick numbers from 1 to n, and we repeat them. So if we concentrate on the first 4 elements, we are actually, with the sync function, we are kind of turning on the slot which contains the same elements in this difference, which means that, okay, assume that this is the first element, the first column of the permutation matrix. If we then will multiply this with our input vector, it means that the 5 will go to position 2, which is what we wanted, actually. So yeah, like this, we already computed the whole permutation matrix. It's already there, and it's encoded column-wise. Okay. Now, the depth of this approach, as you may notice, is actually fine. It's roughly given by the evaluation of the signum function and the sync function. But the sync function doesn't need many levels, actually. The signum does, but if we evaluate it just once, it's okay. And in terms of efficiency, we don't even resort to bootstrapping at all, because we can fix a circuit depth, which is not that large, as we will see in the experiments later. The only drawback of this approach is that we need to repeat the vector n times in the ciphertext. And maybe this is not always, I don't know, allowed in some applications. Maybe if we pick this sorting algorithm as a subroutine in some other application, maybe we cannot really do this. So we also explored, yes? Mm-hmm. Yeah, the thing is, these standard algorithms are heavily based on the data you are plugging in. Like, they are data dependent. So the flux of execution of this sorting algorithm depends on the data you give as input. So I don't know, if I have a 5 here and a 1 here, then I will do something. Otherwise, I do something else. But in FHE, since I do not have 5 and 1, but I have 2 ciphertexts, I have 2 encrypted values, I cannot really change the execution of the program because I cannot read these values. Yeah. I mean, maybe there are other algorithms for sure. Mm-hmm. Yeah, I mean, for sure we can discuss later about this. Yeah, I don't know, honestly. But yeah.
They're supposed to be integers.
Yeah.
CKKS, are they really integers?
Yeah. Okay, so they are, if we go back, yeah, okay. So you're saying the inputs should be Z, actually, values from Z, but in CKKS, there is the error, there are approximate numbers, so they will not be precisely Z, values in Z. You're right, but if we perform a nice approximation before, then also experiments will show that these values will be very, very close to Z. So the error might be like 10 to the -4 or -3, which is okay. I mean, although the function will still work quite nicely. It heavily depends on how well we approximate this function. Because if this is precise, then sync will work well. If this is not precise, then sync will not work well. Which one, sorry? And then you compute the square root. Yeah. Yeah. There is a paper which used this for sorting networks, I think. But I think experimentally, it requires more depth to have a decent precision bits. If you just use the approximation of the sigmoid function as this is. But yeah, I do not have a direct comparisons. But yeah, the square root has the problem that in 0 behaves weird. So, I mean, it goes really. But I might try to also test that other function. Yeah, it might be a good one. I could try this. Yeah, if there are no other questions, I will go to these sorting networks. And in particular, as I said before, these are heavily based on these compare swap operations. And in particular, we will implement this bitonic sorting network, which is this thing in the picture. And notice that this network does not really depend on the inputs we are given. So it's an oblivious algorithm. We just put some vector there, which is a length of a power of 2, and we get out our vector, which is sorted. And if we look at the primitive operation that we perform is this one. And so the question becomes, how can we compute the minimum between two elements or the maximum in FHE? And because, okay, we cannot really evaluate conditional statements or stuff like that. So if we look at previous work based on CKKS, they propose to evaluate this minimum function as I shown here. So they compute the signum. This time it returns 1 or -1. Between x and y, they add 1 and they do over 2. And this will give you 1 or 0 if x is larger than y or not. And then this c value, which we can see as a sort of mask, we can multiply it by y, and we compute 1 minus c times x. And this will precisely mask the value that we want, which will be the minimum one. But again, we are using once more the signum function, which is not something that we really want. So the idea is that do we really need to compute this signum function? Because if we look at the definition, one of the definitions of the minimum function, it can be defined like this. So the minimum between x and y is equal to x minus the maximum between their difference and 0. But notice that maximum between 0 and x minus y is precisely the ReLU function, which is well-defined. So we might, instead of approximated signum, which has this step, this jump, and so on, we can approximate the ReLU function. And notice that if we just plug in the ReLU function inside Chebyshev polynomials, even at low degrees, we can approximate this function pretty easily, which means that we are winning a lot of multiplicative levels because we, again, are not approximating signum, but simply this function. So I'll go now through a quick example, again, for the sorting networks. So assume we want to evaluate this layer. We can do it in a single step, let's say with SIMD computations. And I highlight that we don't really need to repeat these values in our ciphertext. So we only need n slots this time. So the first step is to compute the minimum. And we will use the formula as before. So x minus the ReLU function between their difference. So if we concentrate, like, for example, on 5, then we are computing 5 minus ReLU of 5 minus the rotated left vector of one position, so 5 minus 4. So this will be 1, actually. This is 5, and their difference is 4. We do the same also in this other part, where we have the arrow pointing right. So we are setting the minimum values on the right, on the left position on these two comparisons, which are the comparisons with the arrows going right. Now we can compute the maximum ones using the minimum that we get before. We just simply sum x and y, and then we subtract the minimum between them. But we already computed the minimum, so we don't have to evaluate again the ReLU function. So we get out the 5 and 9. So notice that at this point, we computed the minimums and the maximums, where the arrows are pointing right. But we can actually do the same thing on the arrows pointing left. And again, we do not have to compute again the minimum function because we already did that. So we can just pick the minimum that we have in V1 and just rotate it right. And we apply the same idea to get out the maximum with just x plus y minus the minimum. So with this approach, we evaluate a layer of a sorting network, actually running just once the ReLU function. Yeah, on a side note, just we also have a masking phase later because all these V1, V2, V3, and V4, we have to add them together, but they might have some weird values around, so we just mask them with 1 and 0s in the position that we actually care. So this is an extra thing to do, but we can, again, define roughly the complexity of evaluating of Bitonic layer as the evaluation of the ReLU function, because all the other operations are very fast compared to it. And declining this in the CKKS scheme, the idea is to run a layer, so to evaluate a layer and then to bootstrap. To evaluate a layer and then bootstrap. So as you expect, this approach is slower and the depth of this circuit is way larger with respect to the permutation-based one, but the slots are just n. So yeah, it's a different approach. And moreover, in this approach, we do not have to approximate this signal function. So now we'll just show a few experiments, and all of them are performed using values from 0, 1, uniformly sampled with steps of delta. So we kind of induce a discretization of the values that we can actually represent. And all these experiments have been implemented in the CKKS implementation of OpenFHE and run on this little machine here. Not the best maybe, but yeah. So for the first experiment, we actually want to define the same setup. So we want to compare to MIHP 25, where they sort elements with a delta which is equal to 0.01. And these are the parameters that we are using. And I think the coolest thing is that, like for sorting 128 elements, we really require just 20 multiplication in depth, which is very nice because if we look at MIHP, in order to sort this amount of elements with this precision, they need 65 levels. So it's kind of a nice improvement. Then, yeah, the sigmoid scale and degree are constant, even if we increase n, because this function is computed on the difference between the values, which depends on delta, not on n. While the sinc function, the degree increases with n, because this sinc function is applied on something that comes from the indexing, and the indexing heavily depends on n. So this is the reason why the sinc function, the degree of the sinc function is increased. And then we have this other dti. This is used to correct the elements which are equal, so duplicated elements. I did not discuss about this, but the idea is to find these equal elements using, again, the sinc function. But this comes for free because we can run this operation in parallel with the first indexing phase. So we are not really using any multiplicative depth at that point. So if you look at the performance of this approach, our approach is the pink one. We notice that even, I mean, if we compare to the ST stands for single thread and multi-thread. But if we look at the implementation single thread of MIHP, we're actually winning quite a bit of computational time. And moreover, if we look at the memory requirements, ours are very, very low. And this comes from the fact that we are using really a low depth circuits, which means that we can also use smaller rings without sacrificing security. While in MIHP, they are using larger rings. So, of course, as a side effect, you have larger memory requirements, computational time, and so on. Yeah, so I already said that. While as a second experiment, we want to increase this discretization, and we set delta to be equal to 0.001. And notice that now the numbers are becoming a little bit bigger. For example, this degree of the sigmoid, which goes to 16,000. But still, the circuit depth is fine. It's 24 in the worst case of 128 elements. And if we look at the computational time and memory, it's still, I think, OK. I mean, we can sort 128 elements in 70 seconds, more or less. But this implies a precision up to 0.001, which is a nice precision, I would say. And also, the memory requirements are not that large for being a CKKS circuit. OK, last experiment based on the sorting network. The only actually value that we care of is the degree of the ReLU function, which is not very large. And notice that we can also increase the number of elements without increasing ReLU, because ReLU depends on the difference between two elements, so it depends on delta. So we can also increase n we can still use always the same degree for the nonlinear function. The thing that it's a bit boring in this setting is the bootstrapping, actually, because we always have to run this bootstrapping after each layer. And in fact, if we look at the performance now is, our circuit is the red one, are not better than the MIHP permutation-based one. But if we compare it to the HKC, which is another sorting network based on CKKS, then we are winning a bit of computational time here by a couple of order of magnitude. Essentially, HKC is based on the signum function to make you understand better this comparison. But yeah, so we are winning a bit here. So still a lot of open questions. Like, for example, in the permutation-based approach, can we still avoid the first signum function? Because maybe, I don't know, we can use also the ReLU function somehow. That would be killer, I would say, because at this point, the main bottleneck in the procedure is really the signum function. Also, if we look at the degrees that we are using, can go up to 16,000, which is quite a lot. So also, it would be interesting to compare to a TFHE-based implementation. Maybe the bootstrapping there could help in evaluating this stuff maybe faster, more precise. Would be interesting to compare. And also, I'm not very expert of multi-party computation, but maybe similar arguments can be used to define a sorting algorithm there. I don't know. And lastly, concerning the network-based approach, just one question actually: can this approach be more efficient? Because at this point, the main bottleneck is actually the depth, so the bootstrapping operation. And there is not really something that we can do, at that point. So yeah, that's it. And if you have any questions, I'm here.